Hello, I am Erik van der Ham. I'm a lecturer in building physics at the Faculty of Architecture at TU Delft. In this video, I'd like to talk about the heating demand of buildings. I will first discuss the parameters involved in the heating demand, including the thermal time constant as an important concept. And finally, I will look at a few different heating control strategies. First of all, we're going to look at the steady-state heat balance of a building. In this case, we take a simple house as an example. It's cold outside and the building is heated to a comfortable temperature. So there is a clear temperature difference, which causes heat losses. These heat losses consist of transmission losses through the opaque parts and the windows. This is dependent on the temperature difference between indoor and outdoor and the thermal properties of the building elements. At the same time, there's also a heat loss caused by ventilation. Cold air enters the house, and when there is no heat recovery, warm air leaves the house, and as a consequence, there is a heat loss. Additionally, there is a heat loss caused by infiltration. That is the unwanted leakage of air through the building envelope. On the other side of the heat balance, there's also heat gains. The first example is the sun. When the sun is shining, there's a heat gain through the windows, depending on the amount of solar irradiation, the orientation, and the size of the windows. There are also internal heat loads, for example, all the electrical equipment in the house, lamps, computers, etc., and the people in the house. If all the heat gains are not enough, you need a heating system to provide the required comfortable temperature. To do so, in every room there is a radiator or another heating device. It's controlled in such a way that it maintains the required temperature. If we look at the heat balance on a specific moment during a colder day, it could look something like this. On the gain side, you see the heating system as the main heat source, and a small part is contributed by the sun and the internal heat loads. And on the losses side, you see in this example that the transmission losses are the highest and the ventilation and infiltration is lower. The heat required by the heating system to balance the gains and the losses is what we call the heating demand. This balance is for a specific moment. The heating demand can vary hour by hour, depending on the fluctuating gains and losses, but also depending on the heating strategy. Let's have a look what happens with a conventional heating strategy. During the day, you turn the heating on and this provides the required comfortable temperature. And during the night, when you go to bed, you turn off the heating. And of course, as a consequence, the temperature will drop down gradually. In the morning, when you wake up and you turn on the heating again, the temperature is expected to rise quickly to the comfortable temperature. For that, a large heating power is required. So, in a conventional heating system, there's a high peak in the heating demand in the morning. Let's have a look at the temperature profile for the conventional control strategy. We start in the evening, we turn off the heating, and the temperature will drop down overnight. And in the morning, the temperature will rapidly increase. As soon as it reaches the required temperature, the heating power will be lowered and the temperature will be kept constant. At the end of the evening, the heating is turned off again and the temperature starts to drop. How quickly the temperature drops down, that depends on what we call the thermal time constant. Let's assume a building with the same specific heat losses, but with different thermal capacities. In the graph, you'll see two curves, and the red one indicates how quickly the temperature drops down with a lower thermal capacity, and the green one for a higher thermal capacity. The speed of the temperature drop is determined by the thermal time constant, which is defined as the ratio between the thermal capacity of the building and the specific heat loss. The unit of the thermal time constant is hour. In this example, you can see the lower the thermal time constant, the faster the building cools down. For a typical Dutch dwelling, the heat loss coefficient can be somewhere between 0.05 and 0.5 kilowatts per degree Celsius, and the thermal capacity can be somewhere between 5 to 10 kilowatt hours per degree Celsius. As a consequence, the time constant can range from 10 to 200 hours in a typical dwelling. Now let's compare a few different heating control strategies and see how these influence the fluctuation of the heating demand and the temperatures. First, we have the conventional strategy that we discussed before. Then there's a strategy where we maintain a constant indoor temperature. And thirdly, we look at an ultimate peak shaving strategy where the heating power is constant over the day. To compare these, we did a simulation with some assumptions for the heat loss coefficient and the thermal capacity. The comfort temperature inside is assumed to be 20 degrees and the outer temperature is fluctuating between 2 and 6 degrees. There's no sun or other heat sources, and for the simulation we used a simplified approximation model. First, let's have a look at the effect on the heat supply and the maximum heating demand. In this graph you can see the profiles for the required heating demand over the day for the 3 different control strategies. For the conventional heating strategy, the red line, you see a large peak in the heating demand in the morning. The green line is for the constant indoor temperature, and you can see it's much less fluctuating in the heating demand. Now there is a more or less constant heat supply with variations dependent on the thermal time constant and the outdoor temperature. And obviously for the third strategy, the blue line, there is a constant heating demand during the day. And that's why it is referred to as the ultimate peak shaving strategy. For each of these strategies, the temperatures are different. And here you can see them compared. In the conventional strategy, the temperature drops down during the night. And with the constant indoor temperature strategy, it's obviously constant throughout the day. And with the ultimate peak shaving strategy, the temperature will fluctuate during the day and is dependent on the time constant of the building and the variation of the outdoor temperature. The control strategy also has an influence on the heat losses. You can see in this graph that in the conventional strategy, on average, the temperature difference between indoor and outdoor is lower than for the other 2 strategies. And this temperature difference determines the average heat losses. From this, we can conclude that the conventional strategy has the lowest heat losses and the lowest average energy demand. To recap, we've seen the parameters influencing the heat losses and the heat gains of a building. We've seen how the heating demand strongly fluctuates over a day in a conventional heating strategy, and that the thermal capacity and the time constant have an important impact on the fluctuation of the heating demand and the temperature. We have compared 3 different control strategies, and we've seen there's a trade-off between the peak heating demand, the average heating demand, and the thermal comfort. Thank you for listening.